Welcome back. In this video, we are going to continue our conversation about the chromatic number problem. Recall that where we left it last time, we had a 3 to the n algorithm that used dynamic programming and required exponential space. The first thing that we are going to see in this video is an improvement to 2 to the n in terms of the running time using the inclusion-exclusion formula, but we will continue to use exponential space. Then we will go back to the 3 to the n running time, but this time we will focus on saving space. So we are going to look at a polynomial space approach as well. Now it turns out that you can actually combine these trade-offs to get an algorithm whose running time is better than 3 to the n, and that continues to use polynomial space. So in particular, we are going to see an algorithm whose running time is 2.23 to the n with a polynomial overhead as usual. This is again going to rely on inclusion-exclusion and will use polyspace. We are going to use a black box algorithm for counting independent sets to make the final claim. So in some sense, it's only something that we will be hinting at, but hopefully the overall approach will be clear by the time we get to it. All right, so let's start off with our first algorithm based on inclusion-exclusion. Recall that we have a formula at our disposal which counts the size of the intersection of n sets. So this is what that looked like. And to be able to leverage this, notice that one of the key ingredients is these sets. So what are the kind of sets that we want to be working with when we are thinking about chromatic number? Well, just like for DP, it was useful to think of chromatic number as a partition problem. It turns out that when we are doing inclusion-exclusion, it's very useful to think of chromatic number as a problem about covering the vertex set with independent sets. So let me make this claim explicit, and we'll have a chance to go over it. So I want to say that G can be properly colored with K colors if and only if there are K independent sets whose union is the entire vertex set. Now notice that here I'm not demanding that these independent sets be disjoint, unlike before where we said we want a partition. Here we allow ourselves independent sets that potentially overlap. They need not even necessarily be distinct. And notice that this is true because if G can be properly colored with K colors, we've already seen that it can be partitioned into K independent sets. And any partition is also a cover, so we can just propose the partition, and that gives us the forward implication. For the reverse implication, notice that if somebody gives you a cover with independent sets, then you can transform it into a partition in a natural way. Whenever you have a vertex that belongs to multiple independent sets from this cover, you just have it to commit to one of them. So in particular, you could say that for every vertex, I'm going to place it in the lowest indexed independent set that it belongs to from this cover. This is going to transform the cover into a partition, and therefore if you have a cover, then you also have a partition. Now at this stage, it may feel like we're just playing around with words, and what's the big difference between working with partitions and working with covers? As we will see, it turns out to be really convenient from the point of view of defining these AI sets to actually work with covers. So first of all, notice that if we can count how many covers there are of the vertex set, then we are in business, because we just need to know if there is at least one. that uses k independent sets if we want to know if the graph can be colored with k colors. Of course, previously we were talking about the chromatic number directly, where we wanted the smallest number of colors that can be used to properly color the graph. And here I have implicitly switched to some sort of a decision question where I want to know if a graph can be properly colored using k colors. Notice that if we know how to do this, then we can also solve the optimization version simply by trying all possible values of k. Since k can only take on n possible values, this is just a polynomial overhead and not something we need to worry about. Okay, so with that said, let's talk about what our sets are going to be. So I want to define the set AV for a vertex V in the graph as being the set of all independent set covers with k independent sets which contain the vertex V. So here I'm talking about really partial covers. So let me just write this out and I will go over the definition again. So I'm really looking at collections of k independent sets such that if I look at the union of these sets, then the vertex V is contained in that union. So our universe is really collections of k tuples of independent sets. So that's why universe, any ordered collection of k independent sets, is an element in my universe. Now, these elements in the universe don't necessarily correspond to colorings because we are not imposing the restriction that their union should actually cover the entire vertex set. That condition is something that we are going to get to by basically taking an intersection of all these AV sets over all the vertices of the graph. So notice that this set here, the intersection of all the AVs, is non-empty if and only if there is a covering of the entire vertex set with k independent sets. Why is that? Well, consider any element that belongs to this intersection. This is an element of our universe U, so in particular it looks like some ordered tuple of k independent sets. But because it made it to all the AVs, we know that by definition, the union of these independent sets must contain all the vertices of V. That's the only way that this element of the universe can get a ticket into the intersection. That happens only if it actually belongs to all the AVs individually. So all we need to do now is compute the size of this intersection and check if it's at least 1 or not. If it is, then we are in business and you can in fact color the graph using k colors. But if it's 0, then we have no luck with just k colors and we need to increase our value of k to have some hope of properly coloring the graph, right? So we already know how to compute this intersection. That's given to us by this formula. But to actually compute it, we need to understand what these terms mean. What does it take to compute the individual terms in the inclusion-exclusion formula? So let's take a close look at what this intersection means. So we are thinking about AI complement. So for a single vertex V, what is AV complement? Well, that's going to be all tuples of k independent sets such that V does not belong to their union, right? So that's going to be AV complement. And if we were to intersect AV complement over some V and X, then that means that we're looking at all tuples of k independent sets such that no element of X features in the union. So this condition is true for all V in X, right? So we want to know how many such tuples are there. So take a moment here and see if you can figure out how you can count tuples of independent sets that avoid all vertices in X. Okay, I hope you had a chance to think about that for a minute. Let's say that this is our entire graph G, and let's say this is our subset X. Now what we are interested in counting is the number of tuples of independent sets such that the intersection of X and the union of these independent sets is empty, right? We don't want any element of X to feature in any of these independent sets. Well, notice that that really boils down to figuring out how we can cover elements of G minus X using independent sets. And since we are only working with independent sets sitting in G minus X, we don't have to worry about accidentally including some element of X in our cover by independent sets, right? So we basically focus our attention on G minus X, and let's say that we had access to a bucket which contains all the independent sets in G minus X, right? So this is the collection of all independent sets in G minus X, and let's say that the number of independent sets in G minus X happens to be, let's say, 45. Then notice that the count that we are after is actually 45 to the k, because we have 45 choices for each of these independent sets in the tuple. Remember that we have no constraints whatsoever on these independent sets. This is where it's really helpful that we are looking at covers instead of partitions. So independent sets can even repeat, they can overlap. As long as they are independent subsets of G minus X, we are happy, because we know that their union will not contain anything from X. So everything that we count is a valid contributor to the count that we are after, and anything that is contributing to this count is caught by our argument here. So if you come up with a ordered tuple of k independent sets whose union does not contain anything from X, then each of the independent sets in your tuple is going to be an independent subset of G minus X, and therefore I would have caught it in my count here, right? So in general, basically, if we use S of G minus X to count the number of independent sets that are there in G minus X, then the answer that we are after is basically S of G minus X raised to k. That's what we need to plug in into this formula, and then of course you do your minus 1 raised to size of X and keep track of the running sum. But then the question boils down to, how do we count the number of independent sets in a vertex subset of the entire graph, right? So that is something that we now need to do to be able to calculate the final sum that we are interested in. Remember that we have already talked about exact algorithms for finding maximum independent sets, and we can do something in this spirit to actually count the number of independent sets as well, essentially using a recurrence. So again, let S of y denote the number of independent subsets of y, where y is some subset of the vertex set of our graph. Now, can you think of a recurrence that basically captures the quantity S of y? This would be a good place to pause and think about this. So just as we did with our branching algorithm, one hint is to go into y, set aside your favorite vertex in y, and ask yourself, what are the independent sets that contain y, and what are the independent sets that don't contain y? Think about that for a second and see if you can come up with a recurrence in terms of S itself. So S of a subset gives you a count of all the independent sets in that subset. See if you can use this on subsets of y to count the number of independent sets of y. Alright, so I hope you had a chance to think about that. So notice that if you're thinking about independent sets that do contain this vertex y, then they basically don't contain anything in the neighborhood of y. This is something that we also used when we were doing the branching algorithm. So if we want to count all the independent sets that contain y, then that's essentially all the independent sets of y minus the closed neighborhood of the vertex y. So all the vertex subsets of this region here which are independent will count towards all independent subsets of y that contain the vertex small y. Okay, so that's going to be one part of the count. And what else do we have? Well, we also have to worry about independent sets that don't contain the vertex y, and the number of such independent sets is simply S of y minus the vertex y, right? So we know that all independent subsets here also are independent subsets of capital Y. So we count those as well, and now we have the overall count that we need, right? So basically you can compute S of y for all vertex subsets y using a DP table. But this is why I said earlier that we are still using exponential space, because if you think about this computation, the DP table here is indexed by all vertex subsets, so it is going to take up exponential space. Okay, so now that we have this DP table, we can basically pre-compute the values of S of y for all vertex subsets y, and then we can plug in to our formula here the values S of y raised to k, where y is basically g minus x or v of g minus x when you are going over the term x, right? So that's all that we need to do, and we need to keep track of this running sum over all the 2 to the n subsets, and if that sum turns out to be non-zero, then we can report that we can indeed color G using K colors. But if that sum turns out to be 0, then we know that the answer is no. Okay, so basically we have now an exponential space algorithm that runs in time 2 to the n. The reason for that is that this upfront computation that we did here is 2 to the n time, because notice that we have 2 to the n DP table entries. Each entry is really 2 lookups, and so we are spending 2 to the n time in this pre-computation. And notice that the pre-computation also requires 2 to the n space, because we are basically storing this DP table explicitly, and that's what gives us the 2 to the n running time. We don't have to spend any time in the computation of each entry. The running time really comes from having to populate the entire DP table. Now, going back to where these values are getting plugged in, that's now in this formula here. So notice that when we are computing this sum, it's really a running sum of 2 to the n terms. So we are going to spend 2 to the n time just going over each term. And now let's just think about what does it take to compute a given term. So when we are trying to compute the term corresponding to a particular subset X, then that basically boils down to looking up the DP table entry for v minus x, because we are basically trying to figure out how many covers are there that avoid x. So we are looking for the number of independent sets in the graph induced by v minus x. Now we take that number and raise it to the kth power. That's basically this term. And depending on whether the size of x is odd or even, you decide whether you want to add or subtract that from the current running sum. So getting this value out of the DP table is just a constant time lookup. You're basically looking at a number that might take up to n bits to store. And the reason for that is Remember, these are counts of the number of independent sets that are there in this graph, and this value could be as large as 2 to the n. For instance, if you have a graph that has no edges at all, then every subset is an independent set. So you're storing numbers whose magnitude is potentially exponential in n, and therefore you need polynomially many bits to store such numbers. So by the time you take such a number and raise it to the kth power, you're really looking at numbers that require something like nk bits to be stored, right? Taking such a number and raising it to the kth power can be done in log k time just by divide and conquer, right? So that's straightforward. If you want to compute the kth power, you compute the k by 2th power and basically multiply that by itself to get the kth power, and for the k by 2th power you would do the same with the k by 4th power, and so on and so forth. So that's why that's log k many operations. And so overall, computing the kth power of a value that you have looked up from a DP table is a polynomial time operation, and you're really consuming nk bits to handle all of these operations so far, and you're adding and subtracting numbers that are nk bits long, and you're doing that 2 to the n times, right? So the overall cost of computation here is 2 to the n times poly n, and here you only need polynomial space. For this part of the algorithm, we only consume polynomial space because all we need to do is essentially keep track of this one number that is the final answer. Okay, so that's essentially the 2 to the n exponential space algorithm that we said we will do, and that's now done. Now let's talk about how we can improve this to polynomial space. Well, notice that the exponential space really came up in the computation of the S entries. So this was the pre-computation step where we said that we will look up a DP table that tracks the number of independent subsets of a subset Y. But now, instead of looking this up, we can actually compute it on the fly. That would, of course, mean that we spend more time, but we at least don't consume all this space. So we go back here and we say, well, when it's your turn to compute the term corresponding to x, and you need this value s of v minus x, you just run the whole computation that's given by this recurrence that we wrote down here. Just perform this computation, and you would actually have to perform it fully because now you don't have these values stored anywhere. So that's going to take you time that's roughly 2 to the n. That's if we want to give a lazy upper bound, but the actual time that you need here is going to be 2 to the size of y, right? So notice that the overall running time, if we follow this approach, which is that again we do the counting of the independent sets on the fly instead of looking it up in a pre-computed table, then the amount of time that we need is, well, let's now go over all the subsets of the vertex set. These are all the terms in the inclusion-exclusion formula. We call that when we want to compute the term corresponding to x, we are trying to compute s of v minus x. So that's going to take us time proportional to the size of v minus x. So that's the kind of time that we are looking at. And of course there's like a poly n overhead, which I'm not writing down here. We'll come back and mention that at the end. But here notice that this is basically again a binomial sum. We go through all the k size subsets. There are n choose k many of those, and I can write this down as 1 to the k times 2 to the n minus k, and this again works out to 3 to the n. So for reasons very similar to before, we have essentially a running time whose dominant term is 3 to the n with a polynomial overhead. So the overall time when we do this, computing the numbers of independent sets or independent subsets on the fly is 3 to the n poly n, but what we saved on was space, which is just poly n. Now we're just tracking these nk bit numbers as we go along, and there's nothing else. Now we don't really have to necessarily use the DP that I showed you to count the number of independent sets. We can plug in any algorithm that we know that counts the number of independent sets in a graph. So it turns out that there is an algorithm which runs in polynomial space and counts all independent sets in a graph in time 1.238 to the n, and again poly n. So this is a known algorithm for counting the number of independent subsets of a graph. It's back from 2008, and you can look up the reference. It's a paper of Wallstrom, and there is a reference in the course notes. So basically, I'm not going to be getting into that algorithm, but using it as a black box, we can simply plug in that algorithm instead of our naive recurrence here. And then instead of spending 2 to the v minus x time, we will be spending 1.23 to the v minus x amount of time, because when you are computing this term, the size of the graph on which you are trying to count the number of independent sets is going to be the size of v minus x. So you can simply plug in that running time here, and this will give you 2.23 at the end for exactly the same reason. So that's basically the final status that we have here. We can compute the chromatic number of a graph in time 2.23 to the n using polynomial space. And if you allow yourself exponential space, then you can speed this up further to 2 to the n. Right now, I don't think we know if we can actually manage both 2 to the n running time and polynomial space. So that's something that remains open. But in the meantime, we have these trade-offs that we can contend with, and depending on what we need more, do we need space efficiency, or can we afford the space and we need time efficiency, we can pick one of these two approaches. So I hope you enjoyed the way that we brought in the principle of inclusion-exclusion to solve a problem in graph algorithms. I think it's a really cool idea, and in the assignment you will have a chance to try this out on another problem as well. So I hope you get a chance to practice a little bit more as you go through the course notes as well as the assignments. So that's all that I had to say for now about inclusion-exclusion, and we'll be looking at some other techniques for other problems as we go along. But for now, we will stop here.